Hi, welcome to Algebra 2 Common Core. Today we're going to talk about a special kind of functions called one-to-one functions. In exercise 1, let's consider the two functions f of x equals 2x and g of x equals x squared. We're going to use the domain -2, 0, and 2 for each of them. So I'm going to substitute each value in the domain into each function. So let's start first of all with the function f of x. So when I'm trying to find the output at f of -2, the function says multiply the input by 2, so I get an answer of -4. The function value at 0 is equal to 2 times 0, which is 0, and the function value at 2 is equal to 2 times 2, which is 4. We've already set up a diagram showing the domain of f. We want to put the range of f as well. So the range would be -4, 0, and 4. We're going to map the domain to the range, so let's connect using arrows each input with the correct output. So -2 is mapped to -4, 0 is mapped to 0, 2 is mapped to 4. Let's go ahead and do the same thing with the function g of x. So we want to take the output when the input is -2. So g of -2 would be -2 squared, which is 4. G of 0 would be 0 squared, which is 0. And g of 2 would be 2 squared, which is 4. Now, when we write the range for g, you'll notice that 4 is repeated, so I only need to put the values 0 and 4 into the range. But when I do the mapping, I'm going to say that 0 is mapped to 0, and -2 is mapped to 4, and 2 is also mapped to 4. So you'll notice that there is a difference between these two functions. The difference is each value in the domain of f is mapped to a unique value in the range of f. But for g, two of the values in the domain, -2 and 2, are both mapped to the answer 4 in the range. Pause the video for a minute and write down that description under this answer. Come back and I will have written mine down as well. Check your answer with my answer to part B, the difference between the functions f and g. We can then write down the definition of a one-to-one function. A one-to-one function is a function f of x is called one-to-one if every x value is mapped to one y and every y has one x. Write down this definition and think about how a one-to-one function would look on a graph and in a table. In the next exercise, exercise number 2, we're going to take a look at tables of values and decide when we have functions and when we have one-to-one functions. In exercise number 2, we have to remember, first of all, our definition for a function, that every x has to be matched only with one y value. But then we're going to want to look at which tables of values also show one-to-one functions, where every x has one y and every y has one x. So in the first example, we see that there is a repeat of the x value 4 as well as the x value of 9. Both 4 and 9 do not have unique outputs. So because of that, we would say that this one is not a function. If it's not a function, it can't possibly be a one-to-one function. So we don't even entertain the thought of looking for a one-to-one function. For exercise number 2, when we take a look at all of our inputs, we see that they are all different, but the outputs are not different. I see that both -2 and 0 are both matched to an output of 1. So while this is a function, because every x has only one y attached to it, it is not a one-to-one function. Sometimes we use the symbol 1-1 to stand for one-to-one. In example number 3, we see that this one is a function because every x has only one y attached to it, and this one is also a one-to-one function because every x has one y, but every y also has only one x. For number 4, we see that to begin with, -2 is repeated as an input value with different outputs, so that automatically tells us that this is not a function. So again, as soon as something is not a function, we aren't even going to think about it being a one-to-one function. It can't be a one-to-one function if it's not a function to begin with. Now let's take a look at some graphs and see if we can tell whether we have functions and one-to-one functions for the following 4 graphs. So in part A it says circle the 2 graphs above that are functions. Explain how you know they are functions. You should recall from a couple lessons ago that in order for something to be a function, we have to have a graph that passes the vertical line test. So if I look carefully at all 4 of these graphs, I should see that graph number 1 and graph number 4 are both functions because they pass the vertical line test. So 1 and 4 are the only 2 that are functions. If you look at the graph of number 2, if I draw a vertical line right about here, I see, oh no, the graph is crossing that vertical line in more than one spot, so it's not a function. Same thing happened with the graph of the circle. If I draw a vertical line, there are some vertical lines where the graph crosses it twice, so that makes it not a function. Going over to part B, it says of the 2 graphs that we have designated as functions, which one is one-to-one? Well, when I look carefully at this, I notice that on my parabola, there are certain y values that are repeated. This y value right here is repeated over here. Both of those points have the same exact height. So number 1 is not one-to-one. However, when we look at number 4, every single point has a unique y value. So this y value is different from this y value, is different from this y value. So each x has one y, and each y has one x. So therefore, graph number 4 is one-to-one. So we also have a test that's going to tell us if a graph is a one-to-one function. Remember that the vertical line test tells us whether we have a function. The horizontal line test is going to tell us if we have a one-to-one function. So it works very similarly to the vertical line test. If any horizontal line passes through the graph, at most one time, then the function is 1 to 1. So we're going to use this horizontal line test to tell whether we have one-to-one functions. We're going to begin with the vertical line test to tell us whether we have a function. And then if the answer is yes, then we'll move on to the horizontal line test to determine if we have a one-to-one function. So for example number 1, when we look at this one closely, we see that we can draw a vertical line that crosses the graph more than once. So that tells us right away that this is not a function. I'm not even going to test it for the horizontal line test because it can't be a one-to-one function if it's not a function. For graph number 2, I see that each vertical line only crosses the graph once. So that tells me that this one is a function. So I go on then to the horizontal line test, and I'm looking at my graph, and on my graph I want to see if every horizontal line only crosses once. And I say, uh-oh, there's a horizontal line that crosses many more than once. So while this is a function, it is not a one-to-one function. Looking at example number 3, yes, each and every vertical line crosses just once. So that tells me that I do have a function. If I check the horizontal lines, I see that each horizontal line also only crosses once. So this one is a one-to-one function. Our last one, our parabola, is a function because it passes the vertical line test, but it doesn't pass the horizontal line test, so therefore it is not a one-to-one function. For the last exercise, you're going to need to take a minute and write in the exercise into your note packet where it says exercise number 5. We're going to be talking about the function d of x, which is equal to the absolute value of x minus 5. And we're going to show by example that d of x is not a one-to-one function. If you need to, pause the video so that you've got a minute to write this down and then come back when we're ready to solve. Hi, welcome back. Let's take a look at the function d of x is equal to the absolute value of x minus 5. Now, for this function, it says, let's show by example that d of x is not a one-to-one function. So we want to try some x values and see if we get a repeat of y values. If we do get a repeat of y values, that tells us that each x doesn't have a unique y and each y doesn't have a unique x, so it's not one-to-one. Let's try some values for x. I might even make a table of values for my x and my d of x. You could use your graphing calculator and substitute this in. And in the case of, let's try a few numbers here. For example, what if I try an x value of 3? When I substitute 3 in, I'm getting the absolute value of 3 minus 5, absolute value of negative 2, which is positive 2. So the question is, can we think of another x value that would also give us an answer of 2, an output of 2? Yes, if we think about it, we can try an input of 7, the absolute value of 7 minus 5. 7 minus 5 is 2, and the absolute value is also 2. So we see by example that because these outputs match, this is not a one-to-one function. Now we could have tried any number of points, and again you could have put this in your graphing calculator to find some values in the table of values. The other thing that we can do is take a look at the graph of this. For the graph, and again I'm encouraging you to use your graphing calculator to make the graph, the absolute value graph is our v-graph. And our v-graph is going to have, in this case, a point at an x value of 5. So this graph will look something like this on your graphing calculator. Clearly, if I draw a horizontal line, I see that that horizontal line crosses the graph more than once. So therefore, I can also tell from the graph that it is not one-to-one. So we have numerically shown our solution that it is not one-to-one, and we have also graphically shown that this is not a one-to-one function. In Algebra 2, it's very often going to be important that we can show using multiple representations and prove it in two different ways the way that we did this example. Have a great night, and we'll practice some more with one-to-one functions in class.